Image formation by lenses by M.K. Srivastava, Department of Physics, Indian Institute of Technology, Roorkee, Uttarakhand. See, in the first lecture on geometrical optics, you have seen that both the laws of reflection and refraction follow from Fermat's principle of least time. Now, in this lecture, we shall review diffraction and image formation by thin lenses. A lens is called thin if the thickness is small compared to, for example, radii of curvature of the two surfaces, focal lengths, and image and object distances. We shall also consider coaxial lens systems and so called thick lenses. Now, the line joining the two centers of curvature of the two surfaces of the lens is known as the axis of the lens. It is perpendicular to the two faces at the points of intersection. The first principal focus is defined as the point on the axis such that any ray coming from it or proceeding towards it travels parallel to the axis after refraction. The second principal focus is an axial point such that any incident ray travelling parallel to the axis will, after refraction, proceed towards or appear to come from it. So, this picture shows these features. Primary may be called as first, secondary may be called as second. In the primary, from F, all diverging rays they become parallel after refraction, or if the lens is a concave lens, all these rays which were about to converge to F after refraction again become parallel to the axis. For the second focal point, the rays which are parallel to begin with, after refraction they converge to a point called the secondary focal point or second focal point, second focus, and similarly for the rays which after refraction appear to come from the focal point. Now, the distance between the center of a lens and either of its focal points is its focal length. For a lens with the same medium on both sides, the two focal lengths are equal. Now, a plane perpendicular to the axis and passing through a focal point is called a focal plane. Parallel incident rays making an angle theta with the axis are brought to a focus at a point q prime in line with the chief ray, which is defined, the chief ray is defined as the ray which passes undeviated through the center of the lens. The object and image are called conjugate points, and the planes through these perpendicular to the axis are called conjugate planes. The plane M q and the plane M prime q prime are conjugate planes. M prime is the image corresponding to the object point M, q prime is the image corresponding to the object point q. Now, before we proceed further, we should fix the sign convention which shall be used during these lectures for finding out where the image will be formed for a given position of the object. This is the usual coordinate geometry convention. It is as follows. The point of contact of the center of the lens with the axis is taken as the origin of the coordinate system. Remember, we are talking about thin lenses. Now, the rays are always incident from the left on the refracting surface, incident from the left going towards right. All distances to the right of the origin are positive and distances to the left of the origin are negative, usual coordinate geometry arrangement. The angle that the ray makes with the axis is positive if the axis has to be rotated in the anticlockwise direction to coincide with the ray, and all distances measured upward from the axis are positive and all distances measured downward direction are negative. I mean, this sign convention should be pretty familiar. Now, with this convention, the first focal length f1 is negative for a converging lens, because this point comes on the left of the lens, and positive for a diverging lens, which is a double concave lens, and opposite is the case for the second focal length f2. Let us consider the paraxial image formation by a thin lens. Paraxial means they are very close to the axis, they are not making a large angle with the axis. The thin lens formula is n3 by v minus n1 upon u is equal to n2 minus n1 upon r1 plus n3 minus n2 upon r2. You see, n1, n2, n3 are the refractive indices. n1 is for the medium on the left of the lens, n2 is for the material of the lens, and n3 is for the medium on the right of the lens. Now, the first and the second focal lengths f1 and f2 can be obtained from this expression by putting v equal to infinity and u becomes equal to f1, or u equal to minus infinity and v equal to f2 respectively, and this gives 1 upon f1 is equal to minus 1 upon n1, n2 minus n1 upon r1 plus n3 minus n2 upon r2, and for the second one 1 upon f2 is equal to 1 upon n3, n2 minus n1 upon r1 plus n3 minus n2 upon r2. You see, these capital R1 and R2, they are the radii of curvature of the two curved surfaces of the lens. For a thin lens placed in a medium such that the refractive indices on both sides of the lens are the same, that is n3 is equal to n1, the values of f1 and f2 can readily be obtained by this relation. 1 upon f2, naturally in this case it is equal to minus 1 upon f1. I mean, they are equal in magnitude, there is a sign difference because one focal point is on the left, other is on the right. So, this is equal to n minus 1, n is the refractive index of the material of the lens relative to the medium outside, multiplied by the factor 1 upon r1 minus 1 upon r2. Now, if this factor 1 upon r1 minus 1 upon r2 is a positive quantity, then the focal length f, which is equal to f2, which is the second focal length, is a positive and the lens acts as a converging lens. This is the situation for a biconvex lens. Similarly, if that is a negative quantity, then the lens acts as a diverging lens. Now, the relation between u, v and f is 1 upon v minus 1 upon u is equal to 1 upon f. This relation is very popular and most commonly used for finding out the distance of the image when the object is at a distance u and f is the focal length of the lens. Now, once we know f1 and f2, and therefore, the positions of the first and the second principal foci, the paraxial image can be graphically constructed from the following simple rules. A ray passing through the first principal focus will, after refraction, emerge parallel to the axis. That is the characteristic of the focal point. A ray parallel to the axis will, after refraction, either pass through or appear to come from, depending on the sign of f2, depending on whether the lens is a converging lens or a diverging lens. So, coming from the second principal focus, a ray passing through the center of the lens, called the chief ray, will pass through undeviated. Consider these figures. You see, from the point A, consider that the ray 2, which is parallel to the axis, after refraction passes through f2, which is the focal point. Then a ray from A going through the focal point f1, after refraction becomes parallel to the axis. They meet at the point B, which is the image of the point A. If you consider the chief ray now, this should also reach the point B, APB. Similarly, for the case of the concave lens, a parallel ray starting from A, after refraction appears to come from f2. A ray which was going towards f1, after refraction becomes parallel at the point L, becomes parallel to the axis, and these two meet at the point B, which is the image of the point A. The above graphical procedure is called the parallel ray method. Sometimes another graphical method called the oblique ray method is preferable. The basic principles are the same. Parallel rays incident on the lens are always brought to a focus at the focal plane, and the rays through the center being the only one undeviated, that is the chief ray. Let us consider the picture here. Consider the rays starting from the point M. So, if we actually have rays diverging from M, we can find the direction of any one of them after it passes through the lens by making it intersect the parallel line R prime through A. Let us consider this ray, the ray MT. This is the ray. Now, we wish to find out the refracted ray corresponding to this. So, consider a parallel chief ray and consider the focal plane through f prime. Then one can construct the ray Tx, because the two parallel rays, they must meet in the focal plane. The ray R prime is not an actual ray in this case, and is treated as such only as a means of locating the point x. And once we have located the point x, we extend this Tx to m prime, and m prime is the image of the object at the point M. Newton's formula. You see, this is another relation which is used to relate the object and image distances with the focal length of the lens. The difference here is the distances are not measured from the lens. You see, let x1 be the distance of the object from the first principal focus, not from the lens. x1 will be positive if the object point is on the right of f1, that is as per sign convention, and let x2 be the distance of the image from the second principal focus. So, object distance to be measured from the first principal focus, image distance to be measured from the second principal focus. Consider this picture. I mean, to obtain a relationship in this case, let us first fix up the distances. You see, consider the distance, for example, x2, which is the distance of image from the focal point f2. Usually your object distance u, which is the distance of the object from the center of the lens, the distance of the image I from P is again from the center. Now, to obtain a relationship in this case, we shall make use of the similar triangles. Consider the triangle, for example, AOP and the triangle BIP, and they will give information, some sort of a relationship between the various quantities involved here. So, as I said, considering the similar triangles AOF1 and PLF1, you have a relationship like this, minus y prime upon y, these are the heights of the object points, is equal to minus f1 upon minus x1. These minus and plus signs are as per sign convention. Similarly, from the other set of similar triangles, the ratio minus y prime to y is equal to x2 to f2. The above equation gives the relationship f1 f2 is equal to x1 into x2, and this is known as the Newton's formula. If the medium is same on the two sides, as is the situation in most cases, the formula basically now is x1 x2 is equal to minus f square. Let us consider virtual images. Real images are the ones which can be made visible on a screen. They are characterized by the fact that the rays of light are actually brought to a focus in the plane of the image. A virtual image, on the other hand, cannot be formed on a screen. The rays from a given point on the object do not actually come together at the corresponding point on the image. Instead, they must be projected to find this point. These images cannot be taken on a screen. Virtual images are produced with converging lenses when the object is placed between the focal point and the lens. And with diverging lenses, this is the situation when the object is in any position. Diverging lenses always lead to virtual images. This is a very typical example here. The object is very close to the lens, between the lens and the focal point. If you consider a parallel ray starting from the point Q, then naturally after refraction it passes through the f prime as it should. Then you consider the chief ray from starting from Q, goes through undeviated, and if we extend them backwards, they meet at the point Q prime, which is the image of the point Q. So, that is what it says here. Rays emanating from the object point Q are refracted by the lens, but are not sufficiently deviated to come to a real focus. To the observer's eye at E, these rays appear to be coming from a point Q prime on far side of the lens. The distance of Q prime from the lens is more than the distance of Q. This point represents a virtual image because the rays do not actually pass through Q prime. They only appear to come from there. The ray QT parallel to the axis is refracted through f prime, while the ray QA to the center of the lens, which is the chief ray, is undeviated. Now, these two rays, when extended backwards, as I said earlier, you have seen in the figure, they intersect at Q prime. The third ray in the picture QS, travelling outward as though it came from F, actually misses the lens in this case, but if the lens were larger, the ray would be refracted parallel to the axis as it should. When projected backward, it also intersects the other projections at q prime. Cardinal points of an optical system. See, in the case of a thick lens or in a combination of two or more lenses separated by a finite distance, see, it will be extremely tedious to consider refraction at each surface. To overcome this difficulty, a set of points called cardinal points have been suggested to deal with any number of coaxial refracting systems. The system is treated as one unit without bothering about its actual details. The cardinal points are pairs of focal points, principal points and nodal points. We have already discussed focal points, the first principal focus and the second principal focus. The planes passing through the principal foci perpendicular to the axis are called focal planes. The main property of the focal planes is that the rays starting from a point in the focal plane in object space, they correspond to a set of conjugate parallel rays in the image space. We have seen that. Similarly, a set of parallel rays in the object space, they correspond to a set of rays intersecting at a point in the focal plane in the image space. Now, the principal points and the principal planes, let us see what they signify. There are two principal planes and two principal points. The principal plane in the object space is the locus of the points of intersection of the emergent rays in the image space parallel to the axis and their conjugate incident rays in the object space. The second principal plane in the image space is the locus of the points of intersection of the incident rays in the object space parallel to the axis and their conjugate emergent rays in the image space. We can see it from here. It is clear from the figure that the two incident rays are directed towards H1 and after refraction seem to come from H2. Therefore, H2 is the image of H1. Thus, H1 and H2 are the conjugate points and the planes H1 P1 and H2 P2 are a pair of conjugate planes. Further, H1 P1 is equal to H2 P2. So, the lateral magnification of the planes is +1 unit positive lateral magnification, and that characterizes the principal points and the principal planes. The rays is starting from any point on the axis and cutting the principal plane at given heights from the axis will have their conjugate emergent rays starting from the points in the second principal plane at the same respective height. That is the main thing, at the same respective heights from the axis. All these emergent rays converge to the image point on the axis. Let us consider the nodal points now. These points are a pair of conjugate points on the axis having unit positive angular magnification. Principal points were having unit positive lateral magnification. Nodal points have a unit positive angular magnification. This simply means that a ray of light directed towards one of these points after refraction through the optical system appears to proceed from the second point in a parallel direction. Let us consider. Let H1 P1 and H2 P2 be the first and the second principal planes of an optical system, and let AF1 and BF2 be its first and second focal planes respectively. Consider a point A on the first focal plane. From A, consider a ray AH1 parallel to the axis. The conjugate ray will proceed from H2, a point in the second principal plane, such that H1 P1 is equal to H2 P2 and will pass through the second focus F2. Take another ray now, AT1 parallel to the emergent ray H2 F2 and striking the first principal plane at T1. It will emerge from T2, a point on the second principal plane, such that T2 P2 is equal to T1 P1 and will proceed parallel to the ray H2 F2 as the two rays originate at a point on the first focal plane. Then the points of intersection of the incident ray AT1 and conjugate emergent ray T2R with the axis give the position of the two nodal points N1 and N2. It is clear that the 2 points N1 and N2 are a pair of conjugate points, and the incident ray AN1 is parallel to the conjugate emergent ray T2R. The planes passing through the nodal points and perpendicular to the axis are called nodal planes. Now, the distance between the nodal points N1 and N2 is equal to the distance between the principal points P1 and P2. Further, P1 N1 is equal to P2 N2, which is really equal to F1 plus F2. Now, if the medium on both sides of the system is optically similar, F1 will be equal to minus F2, and this means P1 N1 will be equal to P2 N2 is equal to 0. It means that the nodal points coincide with the principal points. So, in this situation, if you have the same medium on both sides, these pair of points have equal lateral magnification and also equal angular magnification. Let us consider the coaxial lens system, its equivalent focal length and its cardinal points. We consider now here two thin lenses L1 and L2 of focal lengths F1 and F2 respectively. A point object O is placed at a distance u from the first lens, and the final image is formed at I at a distance of v from the second lens. You see, after refraction from the first lens, an intermediate image can be thought of at the point I prime, which then serves as a virtual object for the second lens, and the final image is formed at the point I. D is the distance between the lenses, U is the object distance from the first lens. You see, V prime is the distance of that intermediate image which is formed. So, all those distances are given here. The first image due to the first lens is formed at I prime, as I pointed out earlier, at a distance of V prime from it. So, we have the standard relation 1 upon V prime minus 1 upon U is equal to 1 upon F1. So, this can be written like this: 1 upon V prime is equal to U plus F1 divided by U F1. Now, the image I prime behaves as an object for the second lens. The object distance for the second lens is V prime minus D, and the final image is formed at I. So, here we have the relation 1 upon V. V is the image distance from the second lens. We are writing this relation for the second lens. So, 1 upon V minus 1 upon V prime minus D is equal to 1 upon f2. f2 is the focal length of the second lens, or this can be written as 1 upon V prime minus D is equal to f2 minus V divided by f2 V. Now, from these relations we eliminate V prime and we get a relationship like this: u v multiplied by d minus f1 minus f2 plus u multiplied by f1 f2 minus df2 plus v multiplied by df1 minus f1 f2 minus df1 f2 equal to 0. Now, we treat this problem in alternative way. If alpha represents the distance of the first lens from the first principal plane and beta represents the distance of the second lens from the second principal plane, then the reduced object distances and the reduced image distances are u capital U is given by u minus alpha. Remember, u was the distance of the object from the first lens, alpha is the distance of the first principal point from the first lens. So, capital U is the object distance from the first principal point. Similarly, V capital V small v minus beta is the distance of the image from the second principal point. So, if f is the focal length of the combination of the equivalent lens, we have the standard relation like this: 1 upon capital V minus 1 upon capital U is equal to 1 upon f. We put the values of capital V and capital U. So, write 1 upon V minus beta minus 1 upon U minus alpha equal to 1 upon f. On rearranging this, again we have an equation having terms like u v, u multiplied by minus beta minus f, v multiplied minus alpha plus f, and alpha beta minus beta f plus alpha f equal to 0. We can compare this equation with the earlier similar equation, and that gives us this relationship. 1 upon f comes out to be equal to 1 upon f1 plus 1 upon f2 minus d upon f1 f2. So, this is the focal length of the combination, and alpha beta, alpha is df upon f2, df1 upon f1 plus f2 minus d, and beta is minus df upon f1. So, minus df2 upon f1 plus f2 minus d. So, now the idea is the two lenses are not to be treated separately anymore. We have just one optical system. Object image distances are to be measured from the principal points, and we have the focal length, equivalent focal length of the combination. For the power of the combination, naturally we have this relationship: the total power is equal to P1 plus P2 minus D times, D is the distance between those two thin lenses. So, D times P1 P2. Now, we are in a position to consider a thick lens. Consider a lens of thickness T and made from a material of refractive index mu and placed in air. The radii of curvature are R1 and R2. Look at the thickness between the points P and PQ, that is T. A luminous point object O is situated on the axis at a distance u from the first refracting surface and forms an image at I prime at a distance v prime from P. This image will serve as a virtual object for the second surface. So, for the refraction from the first surface, one can write mu upon v prime minus 1 upon u, which is equal to mu minus 1 upon r 1. That is the standard relation for refraction from a spherical surface. The image I prime formed by the first surface acts as the object for the second surface, and the final image is formed at I. So, here you have the relationship 1 upon mu divided by v minus 1 upon v prime minus t. So, the t is coming because it is a thick lens, is equal to 1 upon mu minus 1 divided by r 2. R 2 is the radius of curvature of the second surface. Now, v prime is to be eliminated between these two equations to obtain an equation in u v, r 1 and r 2, t and u. Now, if alpha is the distance of the first principal point from P and beta is the distance of the second principal point from Q, then taking the capital V is equal to V minus beta, capital U is equal to U minus alpha. We have the lens equation as before, 1 upon V minus beta minus 1 upon U minus alpha equal to 1 upon f. Again, substituting those relations as before and comparing this equation with the earlier equation in u v f alpha beta. Same procedure as we did for the combination of two thin lenses, we get these results. So, 1 upon f is equal to mu minus 1 r 1 minus 1 upon r 1 minus 1 upon r 2 plus mu minus 1 into t divided by mu r 1 r 2. That is the relation defining the focal length. Remember, if t is equal to 0, if it is a thin lens, then this term will not be there. You will have a simple relationship mu minus 1 into 1 upon r 1 minus 1 upon r 2. For a thick lens, this is the additional term which is coming up. Similarly, for the distances of the principal points alpha and beta, if t is 0, you do not have to bother about them, but the center of the lens is the only point. But now, if it is a thick lens, alpha is given by this relationship, beta is given by the next one, similar to those for a thin lens. Now, as t goes to 0, as I pointed out, the lens is thin, the above they reduce to the usual relation for the focal length of a thin lens. Okay, with this, we have come to the end of this lecture. Now, in the next two lectures, we shall take up the defects in the image formation, that is the lens aberrations. Thank you.